A linked list is a common data structure used in software development. It is also a frequent topic in technical coding interviews. In this course, Alvin will explain linked lists and prepare you to use them both in interviews and coding projects.
Hey programmers, Alvin from Structa here. Welcome to our course on linked lists. What I want to do is really get you well prepped for those linked list problems on your technical interviews. So consider this a little bit of a crash course. Like I do in all of our data structure and algorithm courses, I want to go through two pieces of information for every single problem. That is, I want to really draw things out, visualize things, and understand the theory behind a problem before I go ahead and implement the code behind it. All right, so we're going to do a 1-2 punch for every single problem here. So this is going to be an introductory course on linked lists. So I'm going to assume you know nothing about linked lists, but you're not a total beginner to programming, right? So you understand things like while loops, for loops, if statements, and all that jazz. I'm also going to assume that you know a little bit of recursion because I'm going to show you some recursive solutions for many of our linked list problems. And so without further ado, let's jump right in. So what I want to do is start by understanding what a linked list is at a high level bird's eye view. The first thing we'll need to know is that a linked list is a type of data structure, right? So it organizes data, and in particular, a linked list is made up of many nodes. So as our first checkpoint here, we need to first understand what a node is. You can think of a node as just a container for some data. So when we conceptually visualize nodes, we really think of them as some circles that I can put some data inside. Here I'll put a letter or character inside of my node, but of course you can store any data you like. It could be strings, numbers, booleans, or even other objects. Right? And I'm saying that a linked list contains many nodes. So let's say I had a bunch of nodes. And they can all contain different pieces of data. So I have the characters A, B, C, D stored in different nodes over here. And if I wanted to make these nodes comprise a linked list, then what I need to do is add some links. In other words, if I have a node like A, I can make it point to the next node in the data set. That is, A points to B. Right? I can also say that B points to C and C points to D, right? And the term we actually like to use for this is really saying that A's next is B, right? It's going to be very common linked list terminology and a pattern we're definitely going to see in the code later on. And now you can already see why you call this data structure a linked list, right? I have a bunch of nodes linked together. An important thing to note here is about the last node D, right? D is the last node in our linked list. And so under the hood, we can really represent it being the last node by it having its next pointer pointing to nothing. Or more programmatically, we can have its next set to null, right? The null pointer in whatever your language of choice is. So sometimes during this course, I'm going to explicitly choose to draw out the null node or the null reference, just so we can build some very robust code. All right, now that we know what a linked list looks like, I want to introduce some other terminology that you're going to hear, right? So when we refer to the very first node of a linked list, that is the A node in this diagram, I consider that the head. Right? It's a very common term. In a similar way, we can refer to the very last node in a linked list as the tail. Right? So if you hear those words in problems, we're referring to the first node and the very last node respectively. Right? And if you think about it, because I have this sense of different nodes and a first node and a second node, we can think of a linked list as an ordered data structure. In other words, if I started at the head of the linked list, I can just look at this node's next pointer and I can go to the B node. So I can just move to the right. And once I'm at the B node, I can see that B has a next that goes to the C node, and the C node goes to the D node. And the D node goes to the null node, which must mean that I'm at the end of the linked list. So that's a very key characteristic about a linked list, right? A nice property to leverage about a linked list is that it's an inherently ordered data structure, right? If you want to refer to like the positions of these nodes, and we do that programmer thing of starting at 0, I can see that the head has a position of 0, B has a position of 1, and then we just go sequentially throughout, right? So there are 4 nodes within this linked list. I can see that the position of the head is 0, and the position of the tail is 3. And so far, we're probably not seeing the full value of a linked list. Like, when would this data structure have some real utility over other data structures that we know about? In other words, you're probably wondering how a linked list compares to an array, because an array is also an ordered data structure. So let's do that comparison right now. So here I have my linked list up top. And if I wanted to represent, a similar data structure, but in an array form, it would look something like this, right? I have an array in memory, and I know that that array has some indices, right? So there's a really clear analogy here. I know that the indices of an array correspond to the positions of the nodes of a linked list, right? And obviously my linked list is made of many nodes, whereas my array has many elements. The most important difference between an array and a linked list is that an array must be stored contiguously in memory. That means all of your elements in an array are going to be stored like right next to each other in your computer's memory. And that has a lot of consequences in the runtime of different operations across your array, right? So let's say right now I wanted to step through a scenario. Let's say I had the goal of inserting a new element q at index 2 of my array. And the key specification here is I want to insert q at position 2. I don't want to overwrite the current element at position 2, right? So at the start of this operation, I have 4 elements in my array, A, B, C, D. After I do my insertion of q, I should have 5 elements in my array, and they should go A, B, Q, C, D, right? Because I'm inserting some new element at index 2. So how would this algorithm run at a high level in an array? Well, typically, all we would need to do is obviously find the index 2, which is right here. And I know that this is where I need to put the new q element. But I can't just overwrite this value of c because I want to do an insertion, not an overwrite. And so what happens under the hood in your programming language when you perform this insertion operation? Well, we hope that there's still some empty space in the array, and it should occur after d, right? Assuming that there's still space in this array, I would need to shift all of the elements to the right over by 1 index. In other words, I need to put D to the right. I need to put C over 1 position to the right. And now I have perfect room to add this Q at index 2, right? And of course, now D would be occupying a new index of 4 logically. But the important step we took here was to actually insert somewhere in the middle of an array. That could mean that you need to shift over a bunch of different elements in your array, right? So in this very small example, I only had to move over 2 elements of C and D. But let's say you had a very long array and there were, I don't know, 1,000 elements after your insertion index. You would have to shift all of them over one by one. And that is a relatively costly and slow operation for such a simple move of inserting Q, right? So we say that when we insert into an array, that does have an O of n insertion time, right? In the worst case, if you insert at index 0 of an array, that is you're inserting a very first new element, you would have to shift everything over by 1 index in the array. And since there are n elements in the array, you're doing n different shifts. Awesome. Now let's compare that to a similar insertion operation for our linked list. So let's say I still wanted to insert the value of Q at position 2 of my linked list. Well, that means I need to create a new node in memory. And what's great about a linked list is it is not required that the nodes are contiguous in memory. In other words, we can have these like nodes exist anywhere in the space of our computer's memory addressing. And that's kind of a very low-level statement, but the consequence of this is I don't need to do any shifting when I perform this insertion. In other words, how does that work? Well, if I want Q to become position 2 of my linked list, now that I've created the new Q node, I just need to adjust B's next pointer. So I'm going to look at node B and reset its next pointer to point at Q. Then I set Q's next pointer to point at C. And with those small changes, I've actually changed the logical order of nodes within my linked list. It would now be this, right? Q occupies position 2, C occupies position 3, and so on. And what's really great about this is, let's say that there were many nodes after my insertion position. Let's say there were 1,000 nodes. Well, I wouldn't have to actually modify all 1,000 nodes that came after my insertion point. I just need to change about 2 pointers every single time. And because that's a constant number of operations, I will say that a linked list insertion, if we write it correctly, will be constant O of 1 time. So here we see a very tangible difference between our linked list data structure and our array data structure. And there are many more different pros and cons between these two, but for now we'll leave it at that and we can chat more about them as we go throughout the course. I'm sure it's going to come up. But what I want to do for now is talk about the core linked list algorithm. And that's just traversing through a linked list. In other words, how can we just touch and process every node within a linked list? Well, the important thing to know is if you wanted to like give a linked list to someone, or in other words, programmatically pass a linked list into a function, you really only need to pass a reference to the head node of a linked list. Because if I give you the head node of a linked list, by accessing the next property of every node, you could have access to the full sequential list, right? And so to actually implement a traversal algorithm on a linked list, we just need a handful of variables. Most importantly, we need like a current variable, a current reference to look at the current node of the linked list we're iterating through, right? So if I have this current node of A and I want it to go to the next node, I can just look at current.next, right? Or something similar in the programming language of your choice. And I can just set current equal to current.next. Then I would be at the B node. And B also has a next. So I do that again. I'm at the C node. And I can just keep continuing this process, right? Assigning current equal to current.next. Until at some point, once I'm at roughly the tail, current would be D, and so current.next would be this null node, or this null reference. And if I set current equal to next, I'll be right at null, and that can be a perfect condition I can catch. In other words, we can stop the algorithm when current is equal to null. We know that at that point we would have visited every node of the linked list. So as I went through this high-level trace, I was kind of speaking upon this algorithm as if it was an iterative solution, and I'll also show you how you can solve this one recursively. It's really the same line of thinking. At this point, I would want to actually hop into some code so we can see the nuts and bolts implementation of a linked list, as well as the core traversal algorithm through a linked list. All right, let's do this. So here I am in my text editor. I'm going to be doing this in JavaScript, although you should be able to follow along in your language of choice. So the first thing I want to do is just manually build a linked list. And to start, I'm going to need to create a node class, right? So we're going to stay a little bit object-oriented here. Just create a node class. So for me in JavaScript, I need to give it a constructor. And in terms of the properties we're going to need to store inside of an instance of node, I only need two things. I need to store the actual value, but I also need to store a reference to the next node in the linked list if there even is a next node, right? So to my constructor, I'm just going to take in the value, so I can say this.val equals val. And I'm just going to always initialize my next to be null, right? And I can just manually reassign this next property. And if you have this class written, that's all you need to start creating some linked lists, albeit manually. So let's say I want to construct a linked list. I'll just create a few instances of node. So I can create node A, make it a new node. And I need to pass in the value to be constructed. I'll just give it some characters here, maybe some capital letters this time. So the character A. And I'll create a bunch of nodes like this. And so I'll have my B, my C, and my D. And I'll give them some corresponding values. Naturally, I'm storing strings or characters within the values of my linked list, but you can make them, numbers if you want. It's no big deal. What I want to do now is actually link these nodes together. That way I can just have a linked list I can start writing a few algorithms on, right? So typically this part would be kind of taken care for you already. If you were on an interview, you can assume that you're taking in a properly structured linked list. But if I want to just like test some code for myself, what I can do is say things like A's next is going to be equal to the B node, right? So I'm making A's next property now become the B reference. So I'm actually linking these two nodes together, right? A's next is pointing to B. In the same way, B's next is pointing to C. C's next is pointing to D. And there is no other nodes in my linked list, so I'm going to leave D alone. Because I know automatically D's next would currently be pointing to null, which does represent the tail of my linked list. So like visually, I think of this sort of structure. I have A as my head, that points to B, which points to C, which points to D, and technically D points to like null. So I'll be explicit here and just draw that one out. Nice. So now that I have my linked list ready to go, let's go ahead and write our traversal algorithm on it. That is, I just want to iterate through every node of the linked list and maybe just print out the value. Something very, very foundational here. And so I'll maybe choose to make this its own function. I think that would be the best way to go about doing this. So I'll create a nice function here. I'll call it just print linked list. And it's going to take in the head of a linked list. And I'm going to stay kind of abstract here. And I just like to call it head, right? There's my nice empty function. And in terms of how I would actually want to call this function, the client would have to call print linked list and give it like the real head of the linked list, which for me in my little example here is just a reference to the A node. Cool. So I'm actually receiving the head node, which is an instance of node, as the head of my linked list here. And so let's go ahead and now set up our algorithm. So we're going to really just implement the algorithm we just traced out on the whiteboard. So if I want to just traverse through a linked list and print out every node, I'm going to need to continually update a current pointer. So I'll say current equal to the head of the linked list, which means I'm really starting at the very beginning of my linked list. And then from there, how far do I need to go? Well, you want to keep running this algorithm while your current pointer is not equal to null, right? Because if current is not equal to null, then there's some stuff to still iterate through. Now we get into the meat of the algorithm. If I wanted to like print out or process my current node, I'll just console.log here. I'm going to print out this current node's value. Right? And notice that I'm writing all this logic in terms of current, because I hope to update current properly at the end of every iteration. Right? So now that I printed out current's val, what I want to do is update what current is pointing to. So what I should do is set current equal to current.next. And don't be fooled here. This is a very simple variable assignment. Right? So let's run this code, and then I promise that I'll trace through how this actually operates. It's very short code, but really the foundation of most linked list algorithms. So let's give that a run over here. And I hope to print out my characters A, B, C, D. Awesome, and there I have them. So how does this code work? Well, let's try to update and annotate this drawing as we step through the exact code here, right? So I know that in the context of my function over here, I'm really only going to track a really important variable of current. And that starts at the head of my linked list, which is passed in as the A node. So technically, give myself some room here, I would say that the current variable starts by referencing the A node. So I'll kind of represent it like that. It's aligned horizontally, right? Cool. And what I want to do now is consider my condition. So my condition is checking, all right, while this current variable is not equal to null, then run the code inside of the while loop. So if I check that on the first iteration, that condition is true, right? Current is not equal to null, so I can run the code inside, which means I just print out the value of the current node, right? Since current is an instance of node, when I do console.log current.val, I would be printing out the A that was initialized inside of it. So that gives me my first iteration. Now here's the important part. Right now, I know that current is A. So in this moment, that means current.next would be actually referring to the B node. So if I set the current equal to current.next, it has the effect of literally moving this over to the B node. Now I can check my condition again. Is current not equal to null? That's true. So I print out my current value of B and then go to the next. And at this point, the process just continues, right? The C node is still not equal to null, so I print it out over here and go to the next node of D. Now this is still true, right? D is not equal to the null, and so I print out D, and I actually proceed another iteration, right? So right now, current is D, current.next is null. So this would literally happen. I set my current equal to null. But things work out great here, because when I check this condition, I'm going to check, is current not equal to null? In other words, is null not equal to null? And that's false, so I exit my while loop. Right? And that's how I'm able to print out every node of my linked list, right? A, B, C, D. So I think something to draw your attention to right now is how we write this condition. I think the best way and the most robust way to write this code is to check while current is not equal to null. The most common mistake I see people make is they know like generally that your condition should be about like roughly the tail of your linked list. And so they might try to say, well, current.next is not equal to null, right? But that would actually cut your iteration short. If I ran that, I would only really print out ABC, right? Because when I'm at the D node, right, I would be checking, all right, before I even print out D, what's D's next? Well, D's next is null, so I won't even print out D, which is bad, right? So generally when you try to write your algorithms, especially about linked lists, try to write it as like present as possible, right? So I'm not going to do any premature checking of the next node unless I really, really have to. Instead, it's better to actually go to the next node and then exit when you actually are at the null pointer, right? The null node. So let me return this back to its former glory. And we'll just make sure that this still works. This is our classic implementation of a linked list traversal. It's going to be the baseline code for almost all of your linked list algorithms. Let's take this a step further, and I'll show you how you could write this same logic, but recursively. It's really the same logic, you just turn it into a recursive call and a base case, right? So let's go ahead and do this one together as well. And I promise in the next section, I'll give you a nice problem to work through. And so if I want to frame this one recursively, what do I need to do? Well, I like to start with my base case. Your base case should basically be an analogy for like the condition you wrote inside of your while loop. In other words, when are you done with the algorithm? Well, I'm done with the algorithm once I'm looking at null, right? So I'm going to say if head equals null, then I'm done. So just return. Notice that here I'm keeping this argument named as head because I think of a linked list as containing many linked lists. In other words, A is the head of this linked list, but if I look at the sublist inside, B is the head of its own linked list as well, right? And C is the head of a smaller linked list still. So I think that's okay terminology to use for a recursive function. It really shows that you're buying into the recursive nature here, right? Awesome. So I'm going to stop running and just return out once my head is looking at null. So that'd be once I'm at this point, right? But in the recursive case, what I want to do is actually process this node. So if my head is not equal to null right now, then I'm over here, right? What I should do is just print out this node's value, right? Just like I did before, right? I'm just reframing current as head. And if I want to actually progress to the next node, like I did in my iterative solution, I just do a very proper recursive call here. So I'm going to call the same function that actually makes it recursive. And what should I specify as this argument? Well, I just want to give the next node in the linked list, right? So I'm passing in head.next, right? And that would be all I need to do for this one. Very, very short and to the point. So let's run this recursive function. Then I'll help you trace through it a little bit more. Awesome, so it's working. The trace looks almost the same, but I think it's good if we do it side by side with the code over here. And really the key argument we need to trace through is the head over here. So on our top level call, we're really passing in the A node as head. And so I check my base case here. Is head equal to null? That's false. So I go into this console.log, which means I print out the value A. Awesome. And now I make a recursive call upon the next node in the linked list. So if head is A, then head.next refers to B. And since I'm making a call to that next node in this next stack frame, head is B. And I check the condition again. Is B equal to null? That's false. So I just print out B over here and then make another recursive call on B's next, which is C, right? And this process continues all the way down to, let's say, when head is D, right? I check this condition, is D equal to null? That's false. So I go ahead and print out D, which is like the last logical node in my linked list. And I would make another recursive call upon D's next, right? So if head is D, head next is null, and I would indeed make this call. And now I'm back inside of this new call, and I check, is head equal to null? And that's definitely true right now. So I return, that's my base case, and I end my recursion, right? This base case is really, really important. So I want you to compare and contrast these two pieces of code. They really implement the same algorithm, and as we go through these linked list problems, sometimes I'll show you both ways to solve it. Depending on what style of problem you're solving, you might find the recursive or the iterative a little easier to write over the other, which is why I think it's important to practice both, but maybe choose a favorite and decide what you're most comfortable with. But that being said, practice both. All right, let's head back into the whiteboard. Hey programmers, Alvin here. Right now I want to go over an approach for this linked list values problem. So we'll hop right in right here. In this problem, you're going to be given the head node of a linked list. What we want to do is return an array containing all of the values within the nodes of that linked list. And we should do it in order. Bear in mind in this problem, we're given a singly linked list, which means that every node has a pointer to the next node in the linked list. We know that the last node of the linked list would have a next pointer that points to null. But that being said, how can we go about solving this one? Well, this problem is we're just going to have to force you to implement a really core linked list pattern. That is, just traversing through a linked list in order. And so we'll start by attacking this one maybe with an iterative description. So let's say we started from ground zero, right? So we want to create our values array. And to the side, we can just initialize values to be an empty collection. And to implement this core pattern of just traversing through a linked list, we're going to need a variable or just a pointer. And we're going to start at the head of the linked list, right? Bear in mind that our function only takes in the head, but I know the head is like the ultimate starting point of the linked list, and eventually I could access everything throughout the entire list. So I'm going to set my current equal to the head. And what I can do off the bat is just check current's value and add it to my running collection. So I have the A value inside of values now. And since I have access to the current node, I know that if I access its next property, I would have access to the next node of B. So what I can do is set current equal to current.next, basically just moving my pointer to the next node like this. Same thing as before, I can add my current value into the collection. And I'll just proceed in this way, right? Same thing for C, set current equal to current next. And things get interesting once we approach the tail of this linked list. So I'm currently at the D node, and I go ahead and add that value into my values list. What we'll have to do now is consider the scenario when it's appropriate to actually stop our traversal. Well, bear in mind that DeezNext actually points to null. So maybe I'll draw that explicitly just for this drawing. So DeezNext is just pointing to null, which means if I continued this algorithm in the general sense, so I set current equal to current next, that means my current pointer now points to null. And I think that would be a perfect stopping condition, right? So once current is null, we know that we've hit the end of our linked list, and so we're totally done. And if you look at the order of our values, it is indeed the correct order, right? What can we say about the complexity of this algorithm? Well, if we say that n is just the number of nodes in this linked list, then the time complexity is going to be O of n, right? Because we're just really iterating through every node once. And our space complexity, if we consider the output array, it would just be also linear in the number of nodes over here. And so I'll tell you what, this looks like a pretty good strategy that we can go ahead and implement. We'll implement it in two ways. First, I'll show you the iterative version and also show you how to implement this one recursively. Really, both the iterative and the recursive code use the same sort of mechanisms. So I'll see you in the walkthrough video. Hey programmers, Alvin here. Right now I want to go over a JavaScript solution for this linked list values problem. So we'll jump right in and we'll start by implementing, I think, the iterative version that we spoke about in the approach video. So if you haven't watched the approach video, definitely make sure you check that out first, right? And so I'll get the ball rolling over here. What I want to do is use a pointer, really just a variable for me, right? So I'll say let current, I'm going to initialize it to be the head. And I know that the most important pattern I probably need for a linked list is just to traverse in order through a linked list. And the way that looks is I want to keep iterating while my current is not equal to null, right? So just not equal to null. Null would mean the very, very end of my linked list. Nice. And very standard code I need inside is to progress to the next node of the linked list. So I set current equal to current.next. So now I'll think about actually generating the return type for this function. I do want to return an array of all the values, so I should initialize that up top. I'll say let, or maybe const values equals an empty array. And then as I actually iterate through all of my nodes of the linked list, at the tippy top of this while loop, I can just take my current node's value, right? Every node has a .val and also a .next, so I'll take the current node's value and just push it into values, right? So values.push that single val. And once this while loop is done running, I must have hit the end of the linked list, so I can just return the complete values array. So before we run it, one thing I want to always emphasize is for your linked list main logic, it's always important that you try to write your logic about just your current node. So for example, my condition is saying while current is not equal to null. It doesn't say like while current.next is not equal to null, right? You can probably get away with finessing code like that, but it ends up being more clunky than anything. In other words, whenever I try to write my logic for a linked list, I always try to stay very present, right? So just worry about your current node. So what I don't like to see is patterns like this, right? Current.next.val, and try to just shift your frame of reference. Because if you do that, then you're actually kind of assuming that your linked list has a particular length. So instead, I always try to write all of my expressions about simply current, right? So while current is not equal to null, then I push current.val. And then I can just update current to be current.next, and I can be assured that every node is going to be processed in this algorithm. So let's give this a test run now. And if all is well, we can transition into the recursive version now. Awesome. So how can we do this recursively? I'll just do that down below. So the way I would structure this one, just so I get the most optimal complexity, is really with two functions. So my main function will do almost the same thing. It is going to call a helper function. I'll call this helper function maybe fill values. And this function is going to actually do the recursion. So it's going to take in the head of the linked list and also a reference to the values array. So recall that in JavaScript, if I pass any non-primitive types, so basically things like arrays and objects, they are going to be passed by reference, right? So what I want this fill values function to do is to actually mutate the values array, because this main function is going to return it. So what does that recursive function look like? So we'll say fill values. It's going to take in the head and also the values array. I'll start with a base case here. And really what we're trying to do is just translate the same patterns from the iterative code just into their recursive variations, right? And so I know I need to stop my recursion once my head is null, right? So I'm going to check if head is equal to null, then you can stop. So just simply return, right? Really important distinction here is you're going to have a tough time and probably end up with some clunky code if you say if head.next is null, right? So again, I always try to stay very present in all of my code. So don't worry about your next node, just handle yourself, right? Eventually every node will get served here. So if head is null, then nothing much to do, just return and you can stop your recursion. Otherwise, I know that head is not null, so it must be a node, and I need to take that node's value and add it to values, right? So I can say head.val, and I want to push that into the values collection, right? Recall that values is referring to this outer array here. But beyond that, besides this current head, there could be other nodes, right, in the remainder of the linked list. So I can just call recursively fill values, and instead of passing along head again, I need to pass along head.next, right? And that means in that recursive call, I'm kind of jump back around, and now head is referring to the next node, and so on. And then its value is going to be added all the way until we get to the very, very last node. Technically after D, we would hop to D's next, which is null, in which case we would exit due to this base case exactly. And before we run it, just a few issues that I need to fix. I see that I'm missing an equal sign here. And also when I call fill values, of course I need to pass along the same values array, because I know that every call wants to add its value into the same values array there. So we'll give this a test run, see what we get. Cool, and now you also know how to implement this algorithm recursively. So the reason I like to split up my recursive version for this algorithm into two functions is so my recursion doesn't actually have to create like multiple arrays, right? Instead, all of these recursive calls are just adding their values to a single array. If I actually created like copies of arrays all the way through the recursion, I would end up with like an n squared sort of runtime. Cool. So when it comes to comparing these two implementations, they're actually equivalent in terms of their time and space complexity, right? All right, programmers, that's all I got for this JavaScript walkthrough. I want you to practice both the iterative and recursive versions because they're going to both be very useful for the next upcoming problems. I'll see you there. Hey programmers, welcome back. Right now I want to go over an approach we can use for this sum list problem. So in this problem, we're going to be given a singly linked list containing numbers as the values. What you want to do is return the total sum of all the values in the linked list. So for this particular input, we should return a total sum of 20. And so how can we go about solving this? Really just reviewing a core linked list pattern, right? All you have to do here is just traverse in order through the linked list, and you can accumulate a sum. So let's say we start from the beginning. If we initialize some sum variable to 0, we can also just use a pointer that starts at the head of our linked list. And what we can do is we can take current value and add it into our sum, just updating the sum. So I take my current value of 2, add it to my sum. My total sum is right now 2. Then I can set current equal to current next. I can add this 8 into my sum, getting 10. Next iteration, I can add my 3 into the sum, getting 13. Next iteration, I can add 7 into the sum, getting 20. Right? And I know that technically 7 does have a next pointer, and it does point to null. So let's say I drew that out explicitly. What I can do at this point is actually continue my algorithm, and I can make the stopping condition when my current points to null. Right? So in general, we can code this up by saying a loop like, while current is not null. If we talk about the complexity of this algorithm, it's pretty straightforward. We're technically just iterating through every node. So if n is a number of nodes, we have O of n time. roughly one iteration for every node. And then our space complexity here is actually O of 1 if we do this iteratively, right? The only variables we need to maintain are really just current and also the sum variable. And we're just going to store some primitive values in there. So we have a nice constant space solution over here. So the iterative is really straightforward. Just for complete understanding, how can we solve this one recursively? Well, if you solve it recursively, that means you have to call your function many times. And we start with a top level call on the head node of 2. And what this should do is really just call upon the next node, right? So I should call upon head.next. So that should give me a call to this 8 node. And that should call upon the 3 node. And that should call upon the 7 node. And finally, the 7 node should actually call upon its next, which would be the null node. And that will actually act as my base case. I think it's a really great one. What I can do with this base case, right? If my node is null, then I can just return 0. Right? Think of null as if it's an empty linked list. What is the total sum of an empty list? Well, that would definitely be 0. So I'm going to plug in this return value, right? So I'm saying this call to the null node is going to return 0. When we say return, that means return to your caller. So this 0 would actually be returned into the 7 node. And what the 7 node should do is add its current value, right, its own value, into that number, giving 7. And then that returns up the stack. At this point, I return back to the 3 node. 3 can add its value with that 7, giving 10. I'm just returning that up. 8 can do the same, giving me 18. And finally, 2 can add itself into that return value, giving us 20. And that would be the correct answer, right? So there are plenty of ways to implement this one. If we solve it recursively, we're definitely going to have one call for every node within our linked list. So that would be O of n time. And the space complexity would actually be a little more than our iterative. We would have O of n space here because of the call stack, right? Typically, when we analyze our recursive functions, we should include the space utilized for making these recursive function calls, right? So O of n over here. Notice that when we bottom out at our base case, we would have, roughly like 4 or 5 things on the call stack. All right, so those are the 2 strategies I think will code up, and I'll catch you in the walkthrough video. Hey programmers, Alvin here. Right now I want to go over a JavaScript solution for this sum list problem. So I think we'll get things kicked off by implementing a iterative version for this. So I know I want to create a sum and add to it over time, so I'll create that variable. I'll say let sum equal 0. I know by the end of this function, I'm just going to return that total sum. Now I need to lay down my very standard code for just traversing through a linked list. So I'll say let current. I'm going to keep updating this variable over time, and it's going to initialize with simply the head node. And I know that in the loop for this kind of classic linked list traversal, I just want to iterate while current is not equal to null, right? If it's not equal to null, then it's a node, so I can actually look to its next pointer. So I know I'm going to need this pattern, right? Set current equal to current dot next. This actually steps through, the linked list in sequence. But how do I actually want to utilize my current node's value? Well, I just want to take it and add it into the sum, right? So sum plus equals current dot val. And eventually, once I hit the very, very end of the linked list, I know current is going to be equal to null. So I exit the while loop, and I'll just return my total sum. So let's run this. Just a little variation off of our last problem, just doing some computation along the way. Nice, and now I think I'll show you the recursive version, which I quite like. So for your recursive version, it's all about starting with a meaningful base case, right? So the first thing to think about is, all right, typically for my linked list problems, my base case is about my head being null, right? And that kind of represents the scenario where my linked list is an empty linked list, right? If it's null, it means it has no nodes. So what's the total sum of an empty linked list? Well, it's just 0. So I'll check if head is equal to null, then just return 0. And it's important that I think about compatible types here. I know when my linked list actually contains some nodes, then I should return a number. And even in the base case, I should return a number. It's just the case that I return the number 0. Nice. Let's say now we write our recursive code, right? If the head is not null, then it's actually a node. So I can look at its value, right? I could say head.val. And what I want to do is take that number and add it to the sum of the remaining nodes in the linked list. How can I get the sum of the remaining nodes after my current position? Well, that's just about calling your function recursively, right? and passing along head.next, right? So always try to think about your recursive call for the type of data that it returns, right? It gives me back a number representing the total sum of everything starting at the next node. I'll take that number, add it to my value, that should give me my complete sum. So I'll just return it. So I'll give this a shot. And the recursive code is quite short. One thing we should consider, though, when it comes to like an apples-to-apples comparison between the recursive and the iterative, they both have the same runtime, right? They both have O of n. In the case of my recursion, I have n calls. In the case of my iterative code, I have n just iterations in the while loop. But the recursive version also uses n space, right? That's because for recursion, we actually have to add every function call onto the call stack. So I know by the time that my recursion bottoms out at a base case, I would have n calls on the call stack. Whereas in the case of our iterative code, we would actually use only a constant amount of space because I only use a handful of variables here. That being said, I highly recommend that you practice both of these solutions because depending on the problems that we solve, you may find one more natural to use than the other. Hey programmers, before we continue the course on linked lists, I just want to make you all aware of my own data structure and algorithm platform, that is Structy.net. If you haven't noticed already, all of the content that you're watching in this course, as well as some of my other material on freeCodeCamp, is also on Structy.net with a lot of other topics covered as well. So if you go into the course, I cover all of those classic, data structure and algorithm topics with tons of videos for every single one. So if you like my teaching style, I think you'll also enjoy Structy.net. And if you hop into any particular problem, I'll give you a quick little tour over here. So if we go to this insert node problem, like you expect, you can write your code, you can view the problem, you can run your code, see the output. But I think most importantly, what will bring you the most value is my kind of signature of videos, right? So you're going to be able to have a high level approach for every single problem, as well as the code walkthrough. So you get the nuts and bolts code implementation for every single problem. And even still, if you're not like a JavaScripter, I know that this freeCodeCamp video is in JavaScript, you can totally switch the language. So for all of my C++ people in the crowd, doing so, that is switching to C++, would obviously change the prompt in the text editor, but also you'd get different videos, right? Here you see a C++ specific video over here, right? So if you've been enjoying my content and just want to check out more data structure and algorithm material with me, head over to Structy.net. I'll leave a link to the platform in the YouTube video description. And with that, let's head back into our linked list course. Hey programmers, welcome back. Right now I want to go over the approach we can use for this linked list find problem. And I'll show you two ways to solve this one. So in this problem, we're going to be taking in a linked list as input, and we also have a target value. What we want to do is return true or false whether or not the target value is contained within the linked list. So for this particular example, if I'm asking you for a target of C, you should return true because C is definitely within the linked list. In another scenario, let's say I gave you a target of G. In that scenario, you would just return false because G is not a value of this linked list. To solve this one, we're just going to use our classic linked list traversal algorithm. So we'll step through it as if we're looking for C. So in the long run, we expect to give back a true here. Well, I know that they're going to give me the head of the linked list as input, and I'll create a current variable that points to the head node. Of course, I'm going to progressively update this current variable to be the next node over time, right? So what I can do is whenever I'm situated at some current node, I can check if my current's value is equal to my target value. So right now I would check, is A equal to C? It's not, and so I should keep looking through the linked list. I know that current also has a next property, so I'll update current to be current.next. And then I check, is B equal to C? It's not, so I keep going. And finally, I can hit a point where I see that my current value of C is equal to my target value of C. And so I can just do an early return true, right? Once I find a match within my linked list, I can just return my final answer. Now let's say we had the opposite scenario. Let's say that my target was G. We're going to start the algorithm in the same way. We start at current, and when we keep looking through the linked list, and we set current equal to current next, eventually we know that current is going to be equal to null, which sort of signifies that we've hit the very end of our linked list, right? And at this point, once we finish iterating through the entire linked list, we know that we didn't see the target value because we were checking the entire way through. And so at this point, we can do return false. This is a really practical programming pattern, right? Where we check some conditional inside of a loop, and if we find something we're looking for, we'll return true early. Then afterwards, after our loop's done running, we'll return false late. When we talk about this iterative strategy, we know that if n is the number of nodes, we're just going to iterate through every node of the linked list. So we would have a runtime of O of n. And our space complexity here would just be O of 1 because we're just using a constant number of variables. So that was the iterative solution. How can you also solve this one recursively? So let's say we were looking for the target of C and we had a more recursive point of view. So we know we're going to make a top level call on the head node of our linked list, and I can just think about some base cases to use here, right? And I know I need two base cases, right? One that can return true and another that can return false. So for my first base case, I can just simply check, all right, if my head's value is equal to my target, then just return true. And in the opposite scenario, let's say that my head is null, then I should just return false. What I always try to do with my recursive code is to think about my base cases as if they're their own valid inputs. So in particular for base case number 2, if head is null, then that kind of represents the empty linked list. If my linked list is empty, then I can return false because I definitely can't find the target within an empty linked list. So how would this run for our current input of target C? Well, I would check, all right, is A my target? It's not, so I make a recursive call upon B. Same thing, right? It's not. Make another call upon C. And at this point, I see that my current head's value is equal to my target. And so this node is going to return the Boolean true. And I know that this return value is going to return back to its caller of B. And then B is going to pass it back up to A. And of course, A returns it to the very, very top level call. Let's say we had a scenario where our target was not found within the linked list like G, then we can see the other base case fire at the very end, right? So I know I'm going to make a call on A calls B calls C, I still don't find the value, C calls D, and finally, when D looks at its next, it's going to pass along null, right? Because D's next is technically null. And at this point, I have just hit base case number 2, so I can return false. And like before, I return these values up the call stack. When we talk about the complexity of this recursive algorithm, we can say that n is a number of nodes. We're definitely going to have O of n runtime because we make a call for every node of the linked list, but we also have O of n space, right? Because each of those calls, by the time we bottom out at a base case, we would have to store those on the call stack. We know that the worst case scenario is if our target is not found within the linked list. That being said, I think these are two fair algorithms to go ahead and implement, so give it a shot on your own, and if you get stuck, I'll catch you in the walkthrough videos. See you there. Hey programmers, Alvin here. Right now I want to go over a JavaScript solution for this linked list find problem. So we'll jump right in and I'll start by showing y'all the iterative solution. And so we'll start with our pointer variable. We'll say let current equal the head. And we'll just lay down the foundation, right? We know we always need to iterate while current is not equal to null. And while it's not null, if we want to progress to the next node of the linked list, just set current equal to current.next. Now I just need to work in the logic specific to this problem, right? As I check every current node, I want to see if its value, so if current.val, if that is equal to my target. And if it's equal to my target, then I can just return true because I found the thing I'm looking for. What I want to do is return false only after the while loop, right? It's important that I return false after the while loop because only after you check every single node of the linked list can you actually confirm that, hey, the target value is not within the linked list. What you don't want to do is write a like if return true and then else return false, right? This code would be wrong. Because let's say you don't find the target value in the very first node of the linked list, then you would just incorrectly return false without even looking at the rest of the linked list. So none of that. You at least want your code like this. So let's give it a test run, see what we get. Nice, and there we have our iterative solution for this linked list find problem. Let me quickly show you the recursive version of this. It's going to be very similar. So in the approach video, if you haven't watched the approach video, recommend you do. But in the approach video, we mentioned that we can solve this recursively by just using two base cases, right? I'll start with the base case if my head is equal to null, right? So that kind of represents the end of my linked list, or also just an empty linked list. So if head is null, I can't possibly find the target within an empty linked list, so just return false. Now I need my other base case, right? I need my affirmative base case. So if head is not null, then I can look inside of head. I can check if head.val is equal to my target, then I've just found the thing I'm looking for, so just return true. So two base cases here, right? One affirmative and then one that returns false. But let's say neither of these are true, right? So my head is not null and my head value is not equal to my target. Well, then I need to check the rest of the linked list. So here's where I bring in recursion and I check the next node. So linked list find of head.next, and you can pass along the same exact target. So this is going to tell me, all right, is the target found in the next node of the linked list or in the remainder of the linked list? And I know that this call is going to return a Boolean piece of data, right? Either true or false. I just want to pass that up. So this should be good to go. Pretty concise code. Give that a shot. Cool, and there we have a solution that's recursive for this problem. Do bear in mind when it comes to the comparison of the complexities, technically we would prefer the iterative version, right? They both have linear time, but the iterative version has constant space, right? Because I'm just using a current variable, whereas my recursive code uses a linear amount of space because of the call stack. That being said, what I want you to do is practice both of these solutions, and I'll catch you in the next problem. Hey programmers, Alvin here. Right now I want to go over the approach we can use for this get node value problem. So in this problem, we're going to take in a linked list, and what we want to do is also accept an index as input. And what we want to do is really return the node's value at that given index, and we will start counting our indices at 0. In other words, we'll consider the head of our linked list as having index 0. So for this particular example, if I asked you for index 2 of this linked list, you should return the value of the C node, right? So just return the value C. And of course, I could be giving you any particular index as input. So what this question asks is pretty straightforward, but how can we go about solving this one? And so what we can do here is a basic counting algorithm. So we know we want to return the node's value who has index 2. So when we initialize our current pointer to be the head of the linked list, we'll initialize our count to 0. And then from here, it's just our classic logic, right? I know I can set current equal to current.next. And when I do that, I'll also increment my count. So now count is 1. Basically, I have tracked the index of my current node that I'm iterating through. Next iteration, when current goes to C, and of course I increment my count to 2. At this point, I can see that my target index and my count are equal, and so I can just return the value within that particular node. But think about this strategy, it's pretty straightforward in that if n is the number of nodes, the time complexity is simply O of n, right? Because in the worst case, we just have to traverse through the entire linked list. We can also say that the space complexity for this is constant because we're just tracking some simple number variables. So that's how you can solve this one iteratively. How can you also think of this one recursively though? So let's reframe our point of view here. Let's say that we were forced to solve this one recursively, and we know we still want to find the value at index 2. And when I make a call, I know that the top level caller is going to pass along the head of the linked list, so the A node, and also their target index of 2. I can use my classic recursive linked list traversal algorithm. So I make a recursive call on my next node. When I make the recursive call on the next node, what I should also do is pass along the index, but decrease it by 1. So now I'm able to see that, hey, this current node of B has index 1. And if I keep doing this, next iteration, I call upon my next node of C, and I also decrement my index down to 0. Once my index is at 0, that basically means that I want to return this very node, right? So if index is equal to 0, we'll return node.value. That would be our base case. And once we return that value, I know that I'm going to return back up the stack. So the C value returns to its caller, and so on and so forth. Very classic recursive code. So this looks like a nice recursive algorithm. When we analyze the complexity of this, we're going to see that the time complexity is still linear, and the space complexity is actually also linear here. Here we incur a little more space complexity because we're going to be storing every call upon the call stack. So what I want you to do is, on your own, try to give it a shot and implement both the recursive and iterative solutions for this problem. And if you get stuck, I'll catch you in the walkthrough videos. Hey programmers, welcome back. Right now I want to go over a JavaScript solution we can use for this getNode value problem. So hopefully you already watched the approach video. If not, highly recommend you do that. And we'll start by implementing maybe that recursive strategy off the bat. So I'm going to need two base cases here like we said in the approach. And one of them typically is always going to be if our head is equal to null. That means I've hit the end of my linked list, or I have an empty linked list. And what I should do is just return null. That will actually cover a few scenarios. If I look at the examples here, sometimes we may actually get past a very, very large index. So notice here, they're asking for the value at index 7, but the linked list only has 4 different nodes. That means the index of the last node D would be 3, right? 0, 1, 2, 3. So if ever our target index is out of range, then we should just return null. And so this should help me satisfy that, because I'm going to return null once I fall off the edge of the linked list. Nice. We're going to need another base case. What if we actually find the particular node that we need to return its value for? So I know over time I'm going to decrement my index like we said in the approach. So I can check if my index is equal to 0, then simply return this current node. The current node would be head.val, right? Returning its value. Nice. So bear in mind we're counting down here. And so in my recursive code I need to call my function getNodeValue, pass along the next node of the linked list, and then pass along index -1. And I know that this call is going to return the value of the node at the given index, so I should just return whatever that comes back as. If I do a quick sanity check here, bear in mind we're counting downward, so for like this example, example 0, 0, we know that A is going to have an index of 2, right, technically, because we're going downward. And when I make the call for B, it's going to receive index 1. When I call on C, C is going to receive index 0, which means I should just return that back up the stack. So kind of counting downwards here in the reverse, but this should be a nice solution. Let's give this a test run. Bear in mind that this solution has a linear time complexity and also a linear space complexity. We can actually cut down on the space if we write the iterative version. So I'll show you that right now. So the iterative translation you should be very familiar with. You're probably wondering why are we doing such simple problems? Well, it's about to get more difficult, right? To me, it's all about the foundations. So our classic strategy is for iterations, set your current variable to be the head node, right? And I'll just lay out the classic traversal. So while my current is not equal to null, then keep on going. To progress to the next node in the sequence, what I should do is set current equal to current.next. And now I need to work in the problem-specific logic here, right? I know I want to return the node at the given index, and for these iterative patterns, I'll count upward. So I'll set some count variable equal to 0, just like this. And whenever I progress to the next node of the linked list, I'll set count plus equals 1. So I'm counting upward. So when I get to some point when my count is equal to my target index, then I can just return this node, right? So I can return this node's value. So again, we're counting upward in the iterative version, whereas in the recursive version, we counted downward. Nice. Let's go ahead and run this code. There was one thing that probably won't pass, but we'll give it a go to see what happens. So I'm getting a little error here. GetNodeValue has already been declared because of course I have it defined twice. So we'll try that again. Can't redeclare your const variables. So we'll run it. And we're failing in test 02, which is the test where our index or our target index is too large. So here's 02. So we should have our function return null if we can't find the node at the specified index. Right now we're returning undefined, which is happening because this while loop is actually ending, right? We're going to hit the very, very tail of our linked list. And so our while loop's over and we're just going to hit line 16. When we fall off the edge of our function evaluation, we're just going to by default return undefined. So to fix this, it's quite straightforward. Just by default return null. And that should satisfy that scenario. Let's give it a run there. Cool, and there we have an iterative solution. So for this iterative solution, it has a linear time complexity, just like the recursion, but it has a better space complexity, right? Here we consider this constant space because we only use a handful of variables like current and count. That being said, what I want you to do is practice both of these implementations because in the next few problems, it's going to get a little more involved. I'll see you there. Hey programmers, welcome back. Right now, let's go over an approach we can use for this reverse list problem. So in this problem, we're going to take in a linked list as input. What we want to do here is actually reverse the order of the nodes in this linked list. So if our input list contains the values A, B, C, D, in place, meaning we want to mutate the existing linked list, in place we want to actually change the order to D, C, B, A, just ending up with the linked list in reverse order. And in this function, what we should do is also return the new head of the linked list. So technically your function for this input should return the D node. So let's come up with a strategy we can use to solve this one. When it comes to the tools we can use for a linked list, we know more or less we always have to iterate or traverse through the entire linked list. And we know that that requires at least one pointer. Typically we call it current. The trick here is to actually use multiple variables. So let's say I began my classic current pointer pointing at the head of the linked list. What I'll also need is to track the previous node I visited. At the start, because I haven't visited any other nodes, we can make this previous pointer point to null. And we know this entire time, if I have access to current, I also have access to the next node in the list, right? By just accessing current.next. We're just going to label that as a temporary variable here, and we'll call it next, and you'll see why in a little bit. So I know I need to have the long-term effect of just reversing all of the next pointers in this linked list. In other words, I need to make A point to null. And so what I can do is literally just set current.next, in other words, setting the arrow to point to previous, ending up with this. Now it should be abundantly clear why we save the B node with that next variable. Because once we reroute currents.next to point to null, we would lose access if we didn't have that next variable. And so what I can do now is shift my point of view. I can set my current to be the next and set my previous to be the old current. Just shifting my point of view like this. And now I can set current.next to be the previous node once again, rerouting this pointer. And this process continues. As we get toward the end of the linked list, what we have to also remember is technically since D is the old tail of the linked list, this entire time it actually did have a next pointer. It just happened to point to null. And so at this point, I can actually continue my general algorithm, right? I still set current.next to my previous, rerouting this pointer, and I can actually continue one more iteration. If I set current to be the next, it's now the case that current is actually at null, which means we hit the end of our linked list and we can stop our algorithm. If we look at the current state of our linked list, it is in reverse order, right? D points to C, points to B, points to A, points to null. So things are good to go there. And if I wanted to return the new head of the linked list, I can simply return the final value of the previous variable. So that actually works out pretty elegant. If we do the analysis for this algorithm, if we implement this in an iterative way, and we say n is the number of nodes, we know that the runtime is just going to be O of n, really just traversing through the entire linked list once. We can say that the space complexity is constant because we only need a fixed number of variables. So overall, this is a maximally efficient algorithm to reverse a linked list. When we go on to the code walkthrough for this, I'll actually show you how to implement this iteratively and recursively, bearing in mind that the recursive would actually suffer a slightly worse space complexity. But before we get there, try to give this a shot on your own, implement this, and if you get stuck, I'll catch you in the walkthrough video. See you there. Hey programmers, welcome back. Right now I want to go over a JavaScript solution we can use for this reverse list problem. So hopefully you already watched the approach video. If not, I highly recommend it because we're going to implement that strategy pretty closely. So I'll start with the iterative version here. And we know we just need to lay down, at least initially, our classic linked list traversal. So I'm just going to keep my current variable, initialize that to head, and loop while my current is not equal to null. And I know that the basic code would always be set current equal to current.next. That would just move sequentially through the linked list. But now we need to work in a few other variables, right? So the key here is to have some variable, we'll call it previous, and to initialize it equal to null. And if we were wondering why null is a great default value for this previous, just think about what needs to happen on the very, very first iteration of our while loop. So we know that our current is going to be A. And in the long run, we know A's next needs to actually point to null, right? Because it needs to become the tail. So if we initialize previous with null, on the first iteration, we can immediately just say current.next equals previous, right? That would actually have that arrow point to null, which is good to go. But then at this point, we need to make sure that we have some proper references here. So before we just reassign current.next, if we just overwrote it willy-nilly, then we would lose access to whatever the actual next node sequentially was. So I'll save that to a variable. I'll say maybe const next equals current.next. And then after I overwrite it, I can still make progress to the next node of the linked list by simply setting current equal to next. Awesome. So that's looking pretty good. And not only do I need to progress current, but previous should now also point to current, shifting my full point of view. So some pretty tricky logic over here. Let's go ahead and maybe analyze a little bit closer what it's doing. So we'll use some ASCII art here. So let's say we had a linked list that looked like this. So A points to B, points to C. We know we have initially current over here. All right, so current is pointing to A. We know that when I save that next variable, it's going to point to this B over here. So I'll save that. And technically at the very start, we initialized previous to be null. So I'll just use like capital N to represent null. And I know previous is going to point to that like this. Awesome. So on the first iteration, we have all of these variables set up, and I set current.next equal to previous. Current.next is represented by this arrow. So when I set current.next to be previous, it has this visual representation, right? Just setting it the opposite direction. And once I do that, I would actually lose this arrow. And now you can probably see why we saved next for B, right? That way I don't lose access to the rest of the linked list. Cool. At this point, I can set some variables, right? I can make previous the current. So I'll set it like this. Then I also set current to the next. So basically just shift over the point of view. And if you look at the state of my drawing now, things are actually perfectly aligned for the next iteration. I would just set current.next to be previous once again, and so on and so forth, all the way through the very end of the linked list. And like we said in the approach, once we actually end, when current is equal to null, you exit the while loop, and previous would actually contain the new head of the linked list. So I'm just going to return previous over here. It does make sense that previous would be the new head of the linked list, because after I exit the while loop, I know previous is going to be the original tail, right? And if I'm reversing, the tail becomes the head and vice versa. Cool, so really just a spin-off of our classic linked list traversal. I will tell you that the logic here can get pretty tricky, especially with these temporary variables. So we'll give it a test run and see what we get. And hopefully we'll have this nice O of n runtime, O of 1 space solution. Awesome, there we have it. And so what I'll also do now is show you the recursive version. It will have a slightly worse space complexity, although the code is noticeably more concise, so I think it's still worth practicing. So really we're just going to translate the same premise into its recursive version, right? So I'm going to still need like access to two variables or two pointers. And the way I establish that recursively is by using a default argument here. So I'll set previous equal to null. So if you're unfamiliar in JavaScript, this is how you just do a default argument, right? So if someone does not pass in a second argument when they call reverse list, by default, it's going to be set to null. And I can start with a classic base case, right? If head is null, then I've hit the end of my linked list. And what I can do is actually just return previous. For the same reason I returned previous over here, right? Previous would actually be the new tail. And when it comes to actually writing the recursive code, I'm just going to try my best to translate all of these iterative patterns into their recursive analogs. So I'm going to save a reference to the head next, just in a temporary variable. Because if I overwrite it by saying head.next equals previous, I would lose access to it otherwise. So now I at least have a way to call recursively and traverse through the rest of the linked list. So pass in next as the new head, and pass in head as the new previous, really just shifting that point of view once again. If I think about the return value for reverse list, I know it's going to return a node, right? It's going to return, hopefully, the new head of the linked list. So I just want to pass up that return value. Do stay aware in this problem, they say your function should return the new head of the reverse linked list. And this should actually satisfy that. So we'll give this a run. Nice, and here we have a O of n time recursive solution that is also a O of n space, right? So apples to apples comparison, if you wanted to get the most efficiency, you should prefer the iterative version. That being said, I still think there's a nice value to practicing both of these. And this is actually a pretty common interview problem. So make sure you have this down pat before we hop into the next problem. I'll see you there. Hey programmers, Alvin here. Right now, I want to go over the approach we can use for the zipper lists problem. So in this problem, we're going to take in two linked lists. And what I want to do is zipper these two lists together. In other words, I need to, in place, reassign all of these next pointers such that we alternate between the nodes of list 1 and list 2. And it also looks like we should always start with the first node of list 1, and then from that point on, simply alternate. That being said, let's take a look at another example. We don't have many assumptions we can use when it comes to the lengths of both of our lists, except that we know that each list is actually non-empty. But besides that, what if one of my lists was longer than the other? Well, then what I want to do is alternate as much as I can, and then just terminate the linked list with the remaining nodes. So notice I alternate with AQBR, at which point I don't have any more nodes in list 2, so I just take all of the remaining nodes of list 1 and add them to the very end. And so we'll want to keep that edge case in mind when we come up with a strategy for this one. So where do we even start with a problem like this? Well, you should be familiar with our core linked list pattern, right? We just know how to traverse sequentially through a linked list. And so what I can do is actually maintain 2 pointers at a time, right? One for list 1 and another for list 2. So let's say we started stepping through this example. I know I'm past both of these head nodes, head 1 and head 2 respectively, and then from there I can set up some respective current pointers. And so given in the examples, we always want to start with the head node of list 1. So I'm just going to start that down here. And what I'll need to do is also track the tail of my output list, right? Although we're just reassigning all of our pointers in place, we're going to need a reference. That way we can figure out how we can add new nodes to our current output, we'll say. And since I already begin my chain with the first node of list 1, then I need to be sure that I actually progress current 1. And so current 1 should really be pointing at this B node. And so now that I have at least a starting node, how can I come up with a general algorithm here? Well, if you want to establish a simple alternating pattern, then what you can do is just use a counter variable. Have it start at 0, and then based on whether or not the count is even or odd, that would tell you from which list you should take your next node. And so since I already began with a node from list 1, what I should do is whenever my count is even, I'm going to grab a node from list 2. When count is odd, I'm going to grab a node from list 1. So right now count is 0. 0 is technically an even number, and so I'm going to take my next node from list 2. So I look at my current 2 pointer, and it tells me I should just take that Q node and add it as the next of my tail. And so now that I've consumed a node from list 2, I need to be sure I progress current 2 to its next, just like this. And I also need to make progress on some other pointers here. I need to progress my tail also to its next. That way I can get set up for the next iteration of the algorithm. At this point, I need to increment my count by 1. So now count is 1. Since my count is odd, I should take a node from list 1. So I look at my current 1 pointer, and I add B to the tail, just like this. And I make progress on all of my variables, right? So I'm going to progress current 1, I'm going to progress my tail, and increment my count to 2. Since it's even, now I should take a node from list 2. So I take my R from current 2. And when I set current 2 to its next, it's going to become null. When I set tail to its next, it's going to be set to the R. And then I increment my count, so now my count is 3. And now I have an important scenario. It looks like I've exhausted all of the nodes in list 2. We spoke about this scenario, right? Whenever we finish all of the nodes of one of our lists, we should just terminate our output with all of the remaining nodes of our other list, the non-empty list. And so at this point, what I can do is just take my current one, basically this C chain and everything after it, and just put it after the tail in my output. Just like this. And of course I want to complete the connection over here. And this would actually be the correct output. And so overall, our strategy was to maintain pointers to both of our respective linked lists and maintain a count, right? Depending on whether the count is even or odd, then that'll tell me from which list I should take my next node. And along with that, we also need to maintain some tail pointer we can use so we can actually build up the linked list output. Let's talk about the complexity of this one. Since we have two linked lists as input into this problem, we should probably use two terms to describe its complexity. So if I say n is the length of list 1 and I say m is the length of list 2, then I can say the time complexity is the minimum between n and m. Recall that when we just stepped through this algorithm, we really only needed as many iterations as the shorter linked list. Recall the algorithm we just traced through. Now, once we hit the end of one of our linked lists, we know we just finished the algorithm by taking the remaining nodes of the other list and just tack it on to the end. And that finishing step only takes O of 1 time. So really, as soon as one of our linked lists runs out, which will always be, in general, the shorter one, then I can just finish my algorithm. I actually don't have to iterate fully through both of them. And I would still consider this technically, some form of a linear runtime. For the space complexity, we can say that the space here is just constant, right? We're not actually creating any new nodes. We're simply rerouting all of these next pointers. And in terms of our variables, we only use a fixed number of them. And so overall, this seems like a reasonable strategy. What I want you to do is try to code up this one on your own. It's going to be some really interesting code, a new pattern for us, that is. And if you get stuck, I'll catch you in the walkthrough videos. See you there. Hey programmers, Alvin here. Right now I want to go over a JavaScript solution for this zipper list problem. So we'll jump right in, hopefully watch the approach video, and we'll start with an iterative version of this. The way we're going to attack this one is by doing our classic linked list traversal, but do it twice over for head 1 and head 2, simultaneously really. So I'll set my let current 1 to start at head 1, and I'll also set let current 2 to start at head 2. And I'm going to need my main loop just to iterate through the linked list, so I can check while current 1 is not null and current 2 is not null. So notice as soon as one of my linked lists hits its end, this loop would actually stop, right? Cool. What we want to be sure to do is set up also a way to create the output. So if you look at the prompt, we always start with the first node of list 1. So in this particular example, I'm zippering ABC and XYZ. I always start with the A here. And I'm going to use that to get the ball rolling on my resulting list. We're not going to create any new nodes, but we do have to rewire all of these next pointers. So what I'll say is maybe we'll say head over here. And this will be the head of our output, because I know I need to return that by the end. Something like that. And I'm going to start head really as head 1, technically. And then current 1 will actually have to start 1 after that, like we said in the approach. So I'll set current 1 equal to, we'll say, head.next. That'll be a good starting point from there. And in addition to having this head pointer, that's because I want to return, the new head of the linked list, which I guess would be the same as head 1 now that I think of it. So maybe we don't need this variable. But what we do need is a pointer that we can append after, right? So I'm going to say let tail, I think as a matter of fact. I'm going to set tail equal to head 1. So I know head 1 is going to be the first node in my output, and over time I need to add things after the tail, building up my resulting list. So that's looking pretty good. Now we'll go ahead and increment our counter, or add that into the mix here. So we'll say let count, begin it at 0. And depending on whether or not our count is even or odd, that can tell me whether I should take a node from list 1 or list 2. So I think we're ready to hop into our main code over here. I know I should end any particular iteration by, of course, incrementing the count, right? Count plus equals 1. I'm just going to put that down there so I don't forget. And I will start by checking the parity of that count, right? Whether or not it's even or odd. So I'll simply check if count mod 2 is equal to 0. All right, so that means it's even, then else it's odd. So bear in mind, I started my output list with a node from head 1, from list 1. And initially, I start my count equal to 0. So I guess when my count is 0, I'll take something from list 2. So what I can do is take whatever current 2 is pointing at, so current 2, and I want to make that the next of the tail. Right? Tail is helping me build the output. So simply tail.next equals current 2. Nice. Then from there, since I just used up something from list 2, I need to progress that. So current 2 equals current 2.next. And I know that this code over here, when it's odd, is going to be symmetric, just for current 1. And in addition to that, we need to make sure that we also move our tail pointer. That's going to happen in either scenario. So I can put that mutual code over here, I think. I'll say tail equal tail.next. Nice, so this should help me construct my alternating pattern. But what we have to worry about is, based on my while loop, this while loop is going to terminate or end as soon as one of my current pointers hits null. And it could be the case that only one of them is null and the other one is still pointing to some data. And like we said in the approach, what we should do is just tack on all of the nodes of the other list to our final output here. So what I'll do is I'll check, all right, if, let's say, current 1, if it still has stuff, so if it's not equal to null, then I can just take that stuff and add it to the tail. So tail.next equals current 1. And symmetric for current 2, of course. So if I look at the prompt over here, we're thinking about a scenario like this one, right? Here, we know that current 1 is way longer than current 2, or list 1 is longer than list 2. And so by the time we get to the end of list 2, we know that roughly we're going to be at about this C node or this D node in list 1. We just want to take all those remaining elements, looks like D, and add it to the end of that list. Notice I just end in DEF. Cool, and we just need to check both sides of that. Awesome, I think at this point, let's give this a nice test run. You can always debug it together. It's not too long of some code, but it does have some interesting patterns. Awesome, here we have a nice iterative solution for zipperless. For this code, we're looking at a linear runtime and constant space. And so I think what we'll do is, let me also show you how you could solve this one recursively. It's very similar in strategy, somewhat shorter code, and I'll leave it to you whether or not you think it's more simple or not. We will have to concede, though, that for any recursive code, especially for this one, we're going to have some additional stack space used, so we would have a linear space for recursion as well. So I'm going to do my best to translate these patterns. So I know I should stop my recursion. We'll say if head 1 is null and head 2 is null. So that's very similar to what we just said in our iterative version. And if they're null, then you've kind of hit the end. You can just return null. What I have to be sure I do is for my function, it needs to return like the new head of the linked list. And so I'll just have some base case here where I return null. Because basically a linked list contains like many sublists, right? What you should be doing as you solve linked list problems recursively is, if you think of, let's say, this as a linked list, going from A through Z, then going from X to Z is also a linked list. Going from B to Z is also a linked list. So that's how I kind of break down my problem size. So if they're both null, then return null. But what if only one of them is null, right? So what if head 1 is null, right? And that would mean if head 1 is the only one that's null, that means head 2 has some stuff. Well, then just return the remainder of head 2. And make that symmetric for the other side, right? So if head 2 is null and head 1 isn't, then just return the remainder of head 1. And what this base case, or these base cases, will let me do is accomplish some logic just like this, right? How can I take all of the leftover nodes in the case of one of my lists running out and just tack it on to the end, right? If one of my pointers runs out, I'm just going to return the other pointer. Cool, which would be the leftover chain. Now I need my recursive code. So there are a few ways you can write this. Instead of using the modulo trick and checking for even or odd, what I should be able to do is take 2 nodes at a time here. So let's say I know I need to make my head 1 really. So I'm going to return head 1, I think, at the end. And I need to make head 1 dot next point to whatever head 2 is, right? And as soon as I do that, I would actually lose access to the original head 1 next. So I should have saved that. So I'll say maybe const next 1 equals head 1 dot next before I overwrite it. And I guess why not, while we're here, we'll also do the same for next 2. Pretty common thing we have to do for our linked list problems, right? Before you overwrite a pointer, maybe save it in case you need it still. So I'm making head 1 next point to head 2. And then from there, I know I need to call recursively zipper list on next 1. And also next 2 it should be, right? And then from here, I just chained head 1 to head 2. I know zipper list is going to return the head of the remaining linked list. I just need to chain that to head 2. So head 2.next equals that return value. Because again, I'm going to return a node from this recursive call. So this code is looking pretty good. Let's go ahead and test it. It is quite a bit shorter. So we're getting error zipper list is not defined because I need S here. That's on me. Let's give that a go again. Little typo there. Nice, and here we have a nice recursive solution for this. And so just to make sure we're on the same page here, maybe it's worth stepping through at least one iteration together. And so let's say I had these, let's say I had ABC and XYZ. Trace through at least one stack frame of this. So ABC, and then X, Y, Z. All right. So I know in the context of my pointers, I have H1 over here, right? That's going to be head 1. Then I also have head 2, of course. So H2 over here. And what I do is I'm not hitting the base cases for this because I have 2 nodes. And so we save some pointers to their next. So nothing fancy here. I have next 1 over here. I have next 2 over here. And in the core logic of actually alternating, what I do is I take head 1's dot next and point it to head 2. So I don't want to just kind of merge them together in line over here. So kind of separately, although you know I'm not creating new nodes, it would look like this. Head 1 is A. I set its next to X. So that already looks good to go. And then from there, I set head 2's next to whatever the recursive call is when I pass along next 1, next 2. So at this point, I can kind of ignore these, right? So I'll take out just this A node, and now H1 or head 1 points to B, and the same thing over here. H2 points to Y. And let's say we step through this iteration. Well, same thing. I just take head 1, and I know I'm going to return head 1, right? So eventually it's going to return over here. It's going to say B points to Y, right? Because head 1 is B, H2 is Y, head 1.next equals head 2. And that's good to go.